welcome to another Great Calc Basic tutorial. This is part 19 for the PIC16F171 chip family. Hello, my name is Venn. I'm a co-developer of Great Calc Basic. If you like any of these tutorials or this specific tutorial, then please give the thumbs up and subscribe. I need subscriptions, otherwise this is pointless. Let's get started with the deck of slides and into the tutorial. So what we've seen so far is 18 different tutorials covering from hello world, flashing an LED, through to very complicated operations within different IDEs. Just want to wrap that up into the sort of capabilities of Great Calc Basic and bring that together to see what we've covered. So we know a little bit about this chip because we've used most of the capabilities. It's a 16F171, it's a high performance PIC, and it has digital and analog peripherals. We have used those. We've used those in terms of inputs and outputs. We've used the ADC. It has a 12-bit ADC. We've used it as a 10-bit ADC or an 8-bit ADC. Great Calc Basic, you're not just locked in to the 12-bit ADC, but that's a high-performance ADC. We've used the serial interfaces, the I2C interface, the SPI interface, and we've seen those in terms of terminal inputs and outputs. We've used I2C with complex GLCD, and we've used SPI with a complex GLCD as well. And then I chose those because they're very large scale devices. We've looked at pulse width modulation. We looked at it in terms of CCP, PMW, and other modes that Great Calc Basic has in terms of being able to send pulses out, the fixed configuration, the multiple configurations for pulse width modulations. But also, we looked at how you can do 16-bit pulse width modulation. And that's very, very clear. We covered configurable logic cells, CLC. We showed how you can create code that is register based only to take advantage of the CLCs within these chips. The one thing we haven't done is done the op-amp, and I think I'll do a separate video for the op-amp because it's a specialist subject. We've used the 16F17126. That's a 14-pin device, and as it says on the screen, it comes with 8 pins and 20 pins devices. So it's quite a modern chip and quite useful. We've also seen that Great Calc Basic is an open source compiler. It does what it says. It creates code. It creates code for the PICs, AVRs, and Logic Green AVRs. And I touched on this, we did extend and have to support the 16F171 chip family with its small changes, certainly within the ADC configuration, within the pulse width modulation configuration. The rest of it is relatively simple and similar to previous chips. The big difference, quite clearly, is the op-amp. And touched on this yesterday, that Great Calc Basic is a cross-platform common code transactional engine, and I've shown you that before, but we'll look at that in a moment. Because the core compiler itself, whilst it's been developed over the last 10 years nearly, I would imagine it's older than that in terms of where you started, it takes your source code, takes libraries, and turns out on the right hand side an absolute machine code. We also showed that you can interrupt that process. And you can actually, if I can get into PowerPoint, there we go, you can actually select your assembler. And I showed in one of the tutorials how you can use PICAS and MPLAB IDE to actually program, walk the code, debug it, and assemble it, etc. inside of MPLAB-x. So it's quite flexible. Great Calc Basic is a code generator for MPLAB-x. So what I want to show, in summary, is the 16F171 chip family, but also the same code operating across an 18F, an Ardunio, and an LGT. Why is that a good summary? Because it pulls together that everything I've shown you in terms of the demonstrations, are very applicable to a whole range of other chips. That means that if you've want to take advantage of the flat memory model inside of the Q40s, you can. If you wanted to use an Ardunio chassis, then you can. If you wanted to use an LGT for speed, you can. But the code that you're going to generate is it going to be extremely similar unless there is a specific feature within that chip. An example would be the op-amp. The op-amp exists in one family, but not the other three. Therefore, I wanted to show you that as a summary to say this is a cross-platform solution. So here we go. I'm just going to create a user program, use the one we took yesterday, and then we're going to walk the code. Okay, very simple stuff. So what I've got is a program. I'm not going to open up the IDE this time too much. Just no point. Okay, you know how to open GC code, etc. And all I've got on the screen here is a chip line, option explicit. I've defined an LED on port C.1. I've set it to out. That sets the correct input or output for that into a digital port. And why I don't use the words that are commonly used is because if I use the word TRIZ, that's not applicable to all the architectures that we operate under. It doesn't apply in every case. Therefore, let's just talk about setting the LED to out. And then in this program, very simple, flash the LED on and off and wait 1 second. So it basically says LED 1 is not LED 1 and wait 1 second. And if you look in the lab camera, I've got nothing in there. And I've done that for a particular reason because I'm going to slide things in and out, okay? I've just slid that in and pulled out the programming cable, which is spectacular. And so what I've got, the first one, this is low pin count demo board, an LGT 16F171 as it says in our program. I'm going to press F5 to program it. The program is saved by the compiler automatically, and then it's programming it. And we will see an LED flash, and it's flashing every second. How does it do that? Remember right from the start, the compiler knows the frequency that it's set a frequency, and it's done the calculations of an approximation of 1 second delay. Okay, that's so clever. Okay, let's swap that out for something different. We saw this. This is a clone that someone's built, and I believe that this chip is at the 18F. So I will just change our source program. So what I'll do for you is I will stop that flashing because that's a bit distracting by coming into. I will just erase the chip for you in the background. There you go. I've erased it. Okay. Now back in our program, I'm just going to take out this chip line. Why I'm doing that is because you can see the myriad of chips. Hash, chip, space. And it then offers you many chips. Okay, so you can, oops, sorry, didn't mean to go that far. You can select 10Fs, 12Fs, 16Fs, CFs, CRs, etc. And it is a huge list. 16, so I'm going to take the 18F. It's a 16Q40. Hit escape. I've now changed the program to a different chip. It will automatically program that without changing the source code. It's clearly changed the source program in terms of the libraries. It's set the different configuration required for this chip, different frequencies, etc., etc. That's quite clever. Let me pull that one out. We'll go for an Uno. This Uno has got a little LED pack sitting here, and it will make that flash. So let's get rid of our chip line again. hash chip mega. This is a mega 328P. You can actually type in Uno, I believe, and it's running at 16 megahertz. And we're going to tell it that because that's got an oscillator on board. Okay, that's got an external oscillator, so I just need to tell it to do that. So without changing my major source code, I'm going to program it. And if you notice, it's automatically selected the programming port. We'll have a look at that in a moment. And you can see on my finger there is an LED flashing. That means the code has now been written for the Mega 328P. This is a Chinese Logic Green Technologies WAVGAT board, and in here they say it's an LGT. Let's look at our source program. Type the word chip, type in LGT. There's what, 6 different, 6 different options in there. I'll just take the top one, and that will just select the fastest frequency of that particular chip, which is twice as fast as an Uno. Press F5. Now, these are all connected to the same computer because there is a feature that we haven't really looked at, but we're going to look at it in a moment. And as we can see, this LED is now flashing. It's pretty hard to see for you guys, but let me reassure you, it's done it. So what's happening in the background is quite important. I press F4. I'm going to go into the Edit Programmer Preferences. We've seen this before, but we need to have a really good look at it. I can't see why you cannot see what I'm looking at. I'll just go to mine. I'll zoom in on my desktop. There we go. My fault. So what we've got, and I haven't changed the running order of my programmers. This says that an Uno, when it recognizes an Uno board in your source program, it's going to program it at a particular baud rate. How does it do that? If I edit the parameters and look at them, it says it's on communications port 2, which it is, and it says there's a special statement that automatically selects the Uno. It says if it's an AVR, if it's defined as an AVR and it's a chip family, and we've defined a chip family as they're in the help, but essentially a chip family 122 is the LGT. So if it's not an LGT, then use this programmer. Well, quite clearly, most PICs don't meet this configuration. But so this will have to be an AVR and not an LGT, and it will try to program it. My next choice happens to be, if it's a PIC, put it down the PICKitPlus programming line. If it's an LGT, an LGT emulates an AVR. It is a chip family 122, therefore select that one on COM5. If I had an express board loaded, if I wanted to use other programmers, I can set up different parameters. Also, within the compiler, within the tool chain, you can control your programming environment. You can pass to it other parameters like user IDs, other configurations by using this preferences editor. But the essential part is that Great Car Basic is essentially platform independent in terms of the 8-bit environment. Here are the resources. You'll find the tutorials, source code, and the tutorial presentations and other assets up on GitHub with these 2 URLs. You'll also find these in your installation. Finally, 16F171, great little chip family. Get rid of my camera. The only thing that we haven't touched on, as I've mentioned, is the op-amp, but I'll do a separate video on that to find a really good use case for using the op-amp. I think a touch would be very good. So That's what I wanted to cover today. Bit of a summary, bit of a closeout. If you like the tutorials, please like them and subscribe. We'll call that a wrap.